I'm the host.
Yeah.
Thank you, John, and good evening, everybody. Uh, John is our speaker this evening, but I'm going to hand over to Lilith Wynn to do the introductions. But please, would you all mute yourselves? If you don't mute yourself, I will have to do it for you. But don't mute yourself, Lilith. Over to you.
Can I start now? Okay.
Yes.
John was born in Cape Town and educated at St. George's Grammar School, and he got his chemical engineering degree from UCT in 1963. He then joined Sasol immediately and thereafter, and stayed with them, apart from a brief military service, military training, until he retired in 2003. He was general manager responsible for technology, research, development, and innovation. Now, during his career, he spent time in Germany and the USA and Secunda. A highlight of his career was being involved in the design for 4 grassroots gas and coal to liquid plants from concept to operation. He also has served as the president of the South African Institute of Chemical Engineers. He was chairperson of the National Science and Technology Forum and was a councillor for National Advisory Committee for Innovation from 2002 until 2007. As we all know, he is married to Mary, has 2 daughters, 4 grandchildren, and they all are in the Johannesburg area. His interests are classical music, opera, computer technology, and the development of science and technology. He has been chairman of U3A Waterfall for the past 8 years. And as I have told you before, there's an annual mumble and grumble that he's going to resign, but he knows full well now that it's a life sentence. John is also our Hills computer, telephone, internet, apartment hot water system, general technical whiz. Not only does he give a lot of time to U3A, but also to the smooth running of our estate. Our thanks, John, for all that, and of course to Mary for her patience. And I think his talk is going to tie up so well the follow-up to Rosemary's Cole. Thank you, John.
Thank you, Lilith. Yeah, now I'm really confused. Right, there we are. If I may just make a few adjustments here. I think if I do this, you may be able to see me better. Right. Sasol is, interestingly enough, 70 years old. I think it was actually the 30th of September, in other words, just last week. But really, it must be unique in the world as probably the only remaining coal-based fuel chemical conversion plant around. There were many others. There were many attempts. There have been plants operating in America, in Japan, in China, in Germany. But almost all, as far as I know, have been closed and abandoned. It's interesting to find out what makes Sasol so unique. Even today, with all the challenges it seems to have at present, I believe it is set to survive. So what I was saying is that to me, there is a very interesting reason why Sasol is still not only surviving, but doing very well right now, 70 years after it started. And that really created this presentation. So what it is a review of the innovation that has enabled Sasol to succeed over 70 years. And I want to start with some of the history. Sasol is 70 years old today, but its history starts much earlier than that. From the early 1900s, chemists have been exploring the production of chemicals from coal. And in 1925, these two gentlemen, Franz Fischer and Hans Tropsch, two German chemists, at the Kaiser Wilhelm Institute in Mülheim in Germany, were awarded a patent for the what is now known as the Fischer-Tropsch process. It was the production of hydrocarbons from hydrogen and carbon monoxide. Thereafter, in the 20s, many countries, academic institutions all over the world started exploring the possibilities, particularly as at that stage motor car usage was increasing and oil supply was still rather limited. Interestingly, South Africa also started research in that area, and a couple of years later, in 1935, Anglo-Vaal, a company that's been well known in this country for a long time, was operating a torbanite mine in the Eastern Transvaal and produced some small quantities of fuel from this mineral, which is similar to coal. They acquired the rights to Fischer-Tropsch in Germany and even hosted a visit to this country by Professor Fischer in 1937. Then the war intervened, and of course, everything was dropped. After the Second World War, Anglo-Vaal lost interest in Fischer-Tropsch, mainly because all of a sudden there'd been gold found in the northern Free State, and their interest was focused on that, and all their financial resources were going in that direction. That left Fischer-Tropsch to a small number of enthusiasts and academics in this country to keep the interest alive. Then, in 1948, the National Party narrowly won the election and brought with it an increased interest in state-funded industry and industrial development. And as a result of that and the pressure from various groups, in 1950, the National Party was convinced of the value of coal, a coal-based fuel industry for South Africa. And in September, as I mentioned, of that year, the SA Coal, Oil and Gas Corporation was formed. South Africa was far from unique in exploring coal to oil technology, but it was almost alone in being able to move quickly and take the decision to commercialize. A team that had been formed earlier under the leadership of this man, Dr. Rousseau, immediately set to work. German designed gasifiers would be used in this process, while the American Fischer-Tropsch reactors and German Argy reactors would be used to balance production of diesel, waxes, and petrol products. What did not seem to trouble Pierre Rousseau and his colleagues at the time was whether the plant was work. These Kellogg reactors had never been used on a commercial scale, in fact, not on anything approaching commercial scale. The gasifiers would be built on a much larger scale than was used in Germany, and much of the technology had never been commercialized. Such decisions would never be countenanced today by the country's corporate risk advisors. Nevertheless, the plant was constructed in record time, given the limitations of the day, much of the equipment having to be shipped from overseas. Significant changes to the living environment of Sasolburg had to be made. A greenfield site there, a coal mine had to be built, water supplies brought to the Orange Free State. And so one went on with this construction lasting from 1950 until the first fuel was produced late in 1955. That really made the project achieve production in a very short space of time. However, the cost was much higher than budgeted. And in the period from 1955 until 1962, there were many technical problems, preventing the plant from reaching design levels for a long time. This, for a flagship project of a new government, created much negative press, much laughing stock amongst the politicians. Sasol, for many years with no profits, was a disaster. And to me, it was this disaster that created the very core of Sasol's culture, which has lasted for decades and which really, I think, has been the secret of the long-term success. The management at the time determined that the solutions of the problems had to be created, engineered, and implemented by the company itself. It was this pressure that created a culture within Sasol where engineers and scientists were respected, where tolerance for failure was accepted, where there was a willingness to experiment, a willingness to take risks, and in fact, risk-taking encouraged, going along with a very flat but strong management structure, I think was really what enabled things to happen. And it was this culture that has lasted for 7 years. I've just put up there, you can't read it, but it doesn't matter. It's just some of the excuses that are made by management in annual reports as to why things weren't working and can't work. So the result is engineers and scientists were recruited, set to work on the issues. The many technical problems were addressed and were tackled one at a time. There were many, and I'm just going to give a few examples along the way. For example, the major catalyst used in the Kellogg Fischer-Tropsch reactors was an iron powder. This iron powder was produced in one specific iron ore mine in Pennsylvania, the so-called Allenwood iron ore mine, and that's a picture from the 1950s. It was not known why this particular iron ore worked. Iron was the catalyst it used, but it did. By the time the iron ore was mined and shipped to South Africa and added to the reactors, it was found that the results were rather varied and unpredictable. Some batches worked well, others didn't. Some caused major problems in the reactors. And this was why a research project was launched at the time. And over the coming few years, the Sasol scientists determined that it was the impurities in the iron ore that were actually responsible for both the good and the bad performance of this catalyst. And eventually it was decided that the best answer to this was to manufacture the iron catalyst locally, to find a relatively pure source of iron, which happened to be a waste mill scale from Escor, the pile shown in the picture there, and then to add the so-called impurities, today called promoters, which up until now is still done and ensures that that catalyst works properly. And it has also helped make Sasol's catalyst scientists globally recognized as among some of the best in the world. There are many examples of what happened, but I can just say that by the early 1960s, the Sasol plant was performing better than originally expected, and its financial future had been ensured. The picture there just shows very briefly the major components, highly oversimplified, of what Sasol 1 was in 1960, and really just to compare that to what I will show in future. From about 1 million tons of coal, about 5,000 barrels a day of product was produced, mostly petrol diesel, with a little bit of fuel oil, tars, and some byproducts. The second decade in Sasol's history was really one of diversification. This is part of government policy to create a local chemical industry. In this period, Sasol built an ammonia plant to supply the fertilizer industry, created a town gas supply for industries in Johannesburg and the Witwatersrand, built a naphtha-based ethylene plant to supply the plastics industry, a butadiene and styrene plant to produce synthetic rubber. And the final expansion inland was the creation of an inland oil refinery. The Natref refinery was created with two partners, the Total Oil Company and the Iranian Oil Company, the National Iranian Oil Company of Iran. Today, the Natref refinery remains one of the only major inland oil refineries. This means it cannot dispose of its heavy residues, as is done in a usual refinery, into the shipping industry, and has to hydrotreat its heavy oil, which in 1966 was absolutely at the forefront of refining technology. During all this time, Sasol did not neglect its core processes, and much effort was spent to understand and improve and optimize the designs of the gasification and Fischer-Tropsch process. During this time, the M.W. Kellogg Company had got into problems in the other areas and declined to participate further, and as a result, the process was renamed the Sasol synthol process, which is how everybody knows it today. Sasol's engineers and scientists continued to research the process, improve it, understand the fundamentals and the catalysts involved. There were many innovations, but they were mostly minor and incremental, helping to improve the performance of the plant. The third decade was really one of expansion of Sasol 2 and 3. The Yom Kippur War of October 1973 precipitated a large increase in the price of oil. At the same time, the continuing threats or increasing threats of sanctions against made the government request Sasol to consider the possibility of construction of a second plant. Obviously, the economics had to favor such a move, but it was the assurances of the technical personnel that a modernized, more efficient Sasol was possible and that provided the impetus. It was in December 1974 that a second Sasol project was announced by the government at the time. If you look at the oil price, and you can see this chart here, you can see that in 1974, there was a very sudden increase in the price of oil from about $3 or about 20 in today's money to something of the order of nearly $12 to $15 a barrel. That was what made the Sasol possible, and that number would have been about $50 in today's money. The plant was designed to produce about 10 times more hydrocarbon products than the original one. And this was where the innovativeness of the engineers and scientists came into their own. 40 coal gasifiers would be built, each producing nearly 3 times as much gas as the units at Sasolburg. The well-known gooseneck synthol reactors would be nearly 4 times larger, and there would be 8 of them in total. Not so obvious, but amongst all parts of the plant, there were many technical improvements and things that were put in there that were absolutely essential to the success of the undertaking. The expertise of the Sasol staff involved was complemented by engineers, designers, project managers from all over the world, from many contractors, including many well-known global brands, some of which I've shown up here. What one can say further is that apart from international expertise, there was much local expertise as well. The plant was built using mines, conveyor systems, and the entire town, the infrastructure, the concrete cooling water systems, all of this was local technology, and obviously during the entire 5-year construction period, it was local labor, local expertise, and locally trained people that were part of the probably up to 25,000 workers at Secunda at the time. There was much innovation and problem solving required even during the period. For example, when the project was announced, us engineers had no idea where it would be. There was much secrecy around the site because of the need to prevent land speculation. And the result was that after about 9 months of plant design, the site was announced as Secunda, and we found out that it would be upstream of the country's largest water supply dam. Consequently, we had to decide that the plant would have to be designed for no effluent, without any idea how this would be achieved. And it was something that nobody had done before, nowhere in the world. And it took several years of much intense R&D investigation to finally propose a design which would involve a minimum freshwater intake, total recycling of all the effluents, and indeed, other than domestic effluents, nothing going into the watercourses. And I just have a few pictures here of the site as it was developed, and one can see the major size of the construction effort. And what we have in the early 80s was a plant that was completed, successfully commissioned. And that was the result. 40 gasifiers, about 15 million tons of coal, around 50,000 barrels a day of product, and products being, again, mainly petrol, diesel, with some other byproducts that I list there. In 1979, following a few years of gradually increasing oil prices, as you can see on this chart, the oil price again suddenly increased as a result of the fall of the Shah of Iran. The oil crisis that was created, oil prices rose to above $125 per barrel in today's money. Sasol was well placed to consider building a duplicate plant. The timing was excellent because the plant could be duplicated, major orders could just be placed with the same suppliers, construction workers could move from one site to another using mostly the same plans. So this possibility was put on the table. Personally, at the time, I was involved with the planning of the commissioning of the first plant when, between Christmas and New Year of that year, 1998, I was called and told to be ready as an announcement on duplication would be made within 2 weeks. Needless to say, it ruined the rest of a holiday. A further factor in the decision was no doubt the increased threat of sanctions that this Iranian revolution had created. A very positive factor, however, for the long-term future of the company was that in order to raise funds, the existing Sasol plant which was then government-owned, was privatized, freeing the company from direct state control. This was probably the only major petrochemical project anywhere that had ever been duplicated. And it created this truly massive project with more than 25,000 workers on site. The fact that the two plants together would probably produce 35% of the country's fuel needs created the need that petrol and diesel had to be balanced in the proportion for what the market wanted. And that led to some minor changes in the plant's design. But overall, it was absolutely, as this photograph here, which shows both plants, it was an absolute duplication. One plant here and one there, looking almost exactly the same. By 1984, both plants were running. The commissioning of Sasol 3 had been much quicker due to the learning from Sasol 2. One only makes a mistake once, and one could fix it on 4 trains when it happened on the first one only. The entire project, Sasol 2 and 3, was recognized, just as can be seen from this report, by a very well-known consulting organization in the United States, the RAND Corporation, to be one of the very few mega projects in the world ever to be completed on time and on budget. They were truly recognized as a world achievement. Recognition came from everywhere. Executives and politicians from all over the world put Secunda on their must-do lists. Personally, I cannot tell you how many times I was used to escort VIPs around the plant. It was an incredible time. And that was the result of putting Sasol 2 and 3 together, approximately 30 million tons of coal per annum, probably the largest single coal-consuming facility anywhere in one place in the world, producing about 110,000 barrels a day of, again, just mainly petrol, diesel, and LPG with a few byproducts. From here on, I want to try and focus more on technology and less on history. From 1980 onwards, the future of Sasol has just been purely oil price. As one can see, when I come back to this chart again, after the peak of 1979, 1980, there was a gradual reduction in the oil price, a bigger drop in 1986, a long period where it stayed stable, and then the most recent 20 years where it's been otherwise. The result of this slowly reducing oil price was continued pressure on profitability of Sasol. So attention was first focused onto upgrading of co-products. And there were many. Ammonia was converted to fertilizers and then to explosives, adding large amount of volume. Ethylene production was increased. Propylene was produced and then converted to polypropylene and then expanded and doubled. The chemical products, ethanol, propanol, butanol, and other solvents were converted to purified solvents. Phenol and phenolic products were purified. Ethyl acetate was produced in a world first technology development together with Kverna, a British-Danish company, with a technology that was jointly developed and used in Secunda for the first time. Each and every one of these projects were using conventional technologies, but all required adaptation for their use in the synfuel environment that put an enormous amount of responsibility onto the scientists and engineers of Sasol. The next step, as there was increasing pressure on this, was the formation of joint ventures to assist in value adding globally. Sasol formed a joint venture with a German company to increase the production and range of waxes produced. Sasol polymers were formed together with African explosives in this country. Sasol Merichem was formed together with an American company to produce, purify, and expand the range of phenols and phenolics produced. And lastly, along this way, Vista Chemical was acquired. Vista was an American chemical company which had facilities in the United States, in Germany, in Italy, that was very well matched with Sasol's production of oxygenates and olefins. And the result in the end was really Sasol becoming a global giant. This picture, just pulled off a website somewhere, shows the extent of plants and marketing facilities all over the globe. But back to the core technologies. During the entire period where Sasol's major aim had been to ensure the successful completion of Sasol 2 and 3, management focus moved away from the successful and money-spinning plants in Sasolburg, with some adverse consequences. However, to their credit, they did not neglect the support for the ongoing research and development. Teams at R&D labs in Sasolburg had continued to study and develop improvements to their major technologies. One particular area continued to receive attention was the well-known synthol process, originally designed by Kellogg. These reactors were a compromise based on a refining technology called cat cracking, but because the original complex didn't work like it should, they were changed. Sasol scientists, with the new knowledge of how catalysts needed to be formulated, were able to overcome the disadvantages, and they went back to the use of what is called a bubbling fluid bed, starting with much work on a laboratory bench, following it up with a small pilot plant reactor that management managed to find the money to build in Sasolburg in those days. This led by 1990 to a proposal to build a full-size commercial plant, 5-meter diameter, of this so-called advanced synthol process in Sasolburg. And to the credit of Sasol's management, they provided the money. They agreed to the funds to build the 5-meter plant. It was commissioned in 1989, and within a few months regarded as commercial because it worked properly. The advantages shown were enormous, and so impelling that Sasol quickly commenced with a huge project to look at replacing all the gooseneck reactors of the day in Sasolburg with these larger advanced reactors. The operation and maintenance cost savings were huge, catalyst consumption vastly lower, and the greater online time that these reactors were able to achieve could add to production capacity. As a result, as seen here, and that's a small section of just one of 6 reactors being assembled on site, being carried over a bridge somewhere in the Eastern Transvaal. The result was that these reactors were installed instead of the 16 in Secunda. This achievement really shows that you can take a 70-year-old technology, you can modernize it, you can scale it up in an existing plant and create sufficient incentive to do that on the scale that was done. Result was, by 2000, we still had 80 gasifiers in Sasol, but the 16 reactors had been reduced to 8. And instead of just 2 or 3 major products, you can now see the long list of major products that are produced in that plant. And going on to the last phase of Sasol's innovation and expansion, during the 70s and 80s, the production of petrol was the priority at Sasol. However, for the research and development engineers, the search was on for a more effective reactor system, one that was more efficient and cheaper and better to run. And so it became a long-term project to find a better process as well as a better catalyst. The focus this time was on the Argy process, the lower temperature version of Fischer-Tropsch, which was originally built into Sasolburg for the production of waxes and diesel fuel. Simple scale-up was impractical, so Sasol's researchers focused on a process originally attempted by German scientists in the 1940s, which was to have a solid catalyst suspended in a bed of liquid and then to bubble gas through it. This is called technically a slurry bubble column reactor. Sasol called it the Sasol slurry bed process. The benefit here was that after the advanced synthol project, which I just described, the guys in the research department realized they had a 1 meter demonstration reactor that's not used. So a proposal was quickly made, still in the late 80s, to convert this to a prototype slurry bed. Again, quickly agreed by management, although there was absolutely no plan at the time how this development could ever be used. The prototype reactor was commissioned in Sasolburg in 1980. Many questions around the performance were needed to be answered. In particular, the reaction produces a lot of heat, and it needs to be removed in order to keep a constant temperature inside. And of course, the higher the conversion, the more the heat, and the more that it must be removed. So there were really very large challenges to the designers. And then once it was a commercial, an operating plant, the challenge was, what can we do with it? And to make a long story short, Sasol saw the opportunity to expand its wax production in Sasolburg in a project was commissioned in 1993. And what you see there is just a sort of artist representation of what could be done. And that happened. The next phase of that story, though, is the rest of the world, where during the mid-90s, there had been a boom in the discovery of natural gas in large deposits in many locations of the world, which were there to supply the natural gas industry, but there wasn't very much market for these materials. And it created opportunities for projects which could convert that gas to other useful products in remote locations. There is one example of that built by Shell in Bintulu in Malaysia in the early 90s. The Petro SA plant, which was based on Sasol technology in Mossel Bay, was another one. But the Sasol engineers were trying to turn this thing into a concept plant to produce diesel. The diesel fuel would be sulfur-free and contain no nitrogen, and would be compared to normal crude oil diesel of superb quality, and ideally suited for modern diesel engines. And so all these concepts just put together this whole idea, maybe this could be turned into a natural gas-based plant. Without a project in mind, that was done in the early 90s. Through the late 1990s, Sasol started to negotiate with potential partners to do this. It was this two-train, 34,000 barrel a day plant was conceived, and eventually, after a lot of negotiation, many delays occurring because of fluctuations in the oil price. When the oil price drops, nobody's interested in doing anything. Eventually, in 2001, this project in Qatar was approved. A joint venture was formed between Sasol and the Qatar Petroleum Company, and this plant was constructed between 2002 and 2006. A similar sized plant was also built, was planned and built in Nigeria. It is in a much more difficult circumstances in the Niger Delta, and as a result took much longer to construct and was only commissioned in 2014. And that really turned Sasol from the very local Sasolburg plant into now the global chemical and energy producer. The last story, I don't need to talk about that. The last story I would like to talk about today is again back to innovation. This involves a product called alpha olefins. In technical terms, alpha olefins are a range of straight chain hydrocarbons with an olefin bond at one end. They are very highly in demand for high quality plastics as well as for detergents, synthetic lubricants, and many other specialty surfactants. They need to be of extremely high quality, but have a very high commercial value. Normally, these are synthesized in specialty plants around the world, but the opportunity was seen in Sasol as, because the Fischer-Tropsch process produces such a large number of individual molecules, it so happened that these particular quality products in demand are available in the Sasol streams, and purifying them would add hugely to value. The challenge was to find a route to do it that would be economic and technically possible. And so this was the challenge put to Sasol scientists and engineers. The challenge was accepted and was achieved in a remarkably short space of time with some very unique and world-first chemistry and engineering. Explaining this, I think, would be far beyond what I could do in the time I have available. But believe me, the results have put Sasol in an absolutely world-leading position in these specialty markets. And this was certainly part of the reason why Sasol was able to become a major global player it is today. As a final example, and I apologize, this time it's impossible to avoid some technical material, the oxosynthesis process is one that produces oxygenated products from olefins. There is no need to understand the details, except that this route was seen to be potentially useful to Sasol in the long term, as we had all the olefins available. The technology, however, was very unique and very tightly controlled by one or two major manufacturers in the world, making it unlikely that Sasol would be able to access that. In the mid-90s, without any knowledge of where and how it could go to, it was agreed by Sasol management that technology had a long-term potential and that it should be included in a research portfolio. This was done. Doctoral students were given bursaries to work in the field. A well-known catalyst scientist was recruited from overseas to set up a homogeneous catalysis, as this subject is called, research program in Sasolburg. A partnership was formed with the chemistry department of the University of St Andrews in Scotland. We got that through the management. We always thought part of the reason was the attraction of sending the CEO to go and play golf at St Andrews. But nevertheless, the things went ahead. After nearly 10 years of working in this program, and only in 2005, Sasol published a patent for a process to produce the valuable chemical octene-1 from ethylene based on this research. And once again, these research results were not just published for information, but Sasol immediately launched a large-scale scale-up and pilot plant project to gain the information needed to turn this absolutely pure research result into a full-scale plant. And this involved taking 4 molecules of ethylene and combining them with a catalyst so that it would very carefully combine them into a single molecule, 8 carbon atoms long, so-called octene, but again, absolutely straight chain with the olefin bond at the end. And I can't explain it, but the catalysts that are needed to do that are extremely unique. I have now forgotten some of my pictures, but they're not showing anything. Just finally, also at the same time, Sasol 1, with the discovery of natural gas in Mozambique and the plan to build a pipeline for gas from Mozambique to the Witwatersrand, it was decided that Sasol 1's future would be in natural gas and maybe not in coal. And by 2001, 2002, Sasol had been converted to use natural gas and not coal, to convert it in an autothermal and oxygen reformer. And Sasol 1 today, instead of making petrol and diesel, is producing purely specialty products, waxes, paraffins, some ammonia, methanol, acrylics, a very different Sasolburg from what it was. The many stories that I've related today illustrate that the qualities that have defined Sasol culture from the start were there. Sasol had this long strategic belief in the value of research and development of engineers and scientists, and has on many occasions taken on projects from small beginnings on a laboratory bench to world scale. Sasol had been prepared to take the considerable risks that other chemical companies would shy away from. They were able to reach decisions quickly, take very brave decisions, attack the technology challenges with determination, ingenuity. In other words, it's mostly South African engineers and scientists, not only with a steady stream of challenge and opportunity, but also with an unusual freedom to innovate. The result is that it attracted and retained many of the finest minds. And I like to bring this together in my final slide with a management research paper that was published in the Harvard Business Journal, I think last year, listing, and this was based on research around today's major innovative companies, Google, Apple, Tesla, and so on, where they define the characteristics of an innovative culture. And I think if one looks at those, they describe very well the reason for success for the past 70 years. And the result has brought a small government-owned technology company using imported and imperfect technology to being a global force in the chemical industry, the largest producer of coal and gas-based liquid fuels in the world, with a footprint everywhere. Unfortunately, that growth and success that Sasol achieved brings modern commercial governance practices and codes that might have reduced the effectiveness of the culture. However, I believe that the company will go to further success in the future years, and the future challenges that lie ahead, and the very real challenges that are present for an organization set in coal today. So with that, thank you very much.
Lilith, would you like to unmute yourself and take questions? Just while Lilith is doing that, there were a couple of questions on the chat from Jill, Jill asked, what is the volume of a barrel of oil? And do you know the approximate percentage of Sasol fuel supply to South Africa today? Did you get that,
right.
John?
That's easy. Sorry, a barrel of oil is about 220 liters. So they're about 5 barrels in a ton or in a cubic meter.
And the percentage?
As I said, at peak, Sasol produced about 35% of the country's fuel. But obviously since 1984, consumption has increased quite considerably, and some of the Sasol products have been diverted into chemicals. So we are probably dependent on Sasol for maybe 20% of our fuel today.
Thank you, John. Lilith, can I continue? There's another chat question.
No, Rob, you carry on, please. Much better if you do it. Thank you.
From Rosemary. John, what was your role in all this? When did you join Sasol and until when? That's from Rosemary.
As stated in that CV, I had a 40-year service at Sasol, and part of that was not just lack of innovation on my side and wanting to go elsewhere, but was really the result of every time one got bored, there was a new challenge. I probably spent the first 10 years just doing things any engineer does. In the early 70s, I was involved with consulting Sasol's technology overseas in a program where the Americans were very interested in turning coal into gas and into other things. I was the probably 5th or 6th employee to be assigned to the Sasol 2 project in 1975. By the time Sasol 3 came along, I was put in charge of the process design, the conceptual designs, not the execution side of things. And really went from there to running or being in charge of research, development, and most of the creative, the innovative side, the front end side of engineering at Sasol.
Thank you, John. Are there any other questions?
Yeah.
You can either unmute yourself. Yes.
Hello, Rob, can you hear me?
Yes, we can hear you.
Tony Shardlow.
Hello, Tony.
John, thanks very much indeed. That was remarkable talk. Thank you, appreciate it. Recognizing that you can't make an omelette without breaking eggs, 32 million tons of coal per annum being processed. How environmentally friendly is this in respect of global warming and so on and so forth? Can you comment? Oh, and a rider to all of this. Of course, where is Sasol when motor cars transfer to electrical energy? Thanks very much indeed, John.
I'm not part of Sasol at the moment, and I don't know what's happening. The environmental standards of the past 70 years have obviously changed all the time and keep on changing. It is true that Sasol 2 and 3 were built in the mid-80s, early 80s, and so probably not suitable totally for the needs of today. You asked about the future. Well, I think Sasol has already accepted the need to improve its efficiency. It looks like they have already done that to some extent. They are looking at increasingly using renewables. How far that can go remains to be seen. How far electric vehicles take over from other transport means is also something that's in the future. But it is indeed true that if the world is really to be net zero carbon, we're not going to be able to run intercontinental aircraft with batteries.
Thanks, John.
But there is the possibility to turn Sasol's fuel into a very highly renewable fuel by increasing the amount of green hydrogen, hydrogen from solar power or from renewable power into it, meaning there are ways of going further that way. Another technology I'm sure that Sasol is looking at very deep, in much detail at the moment, is carbon capture and storage. It is already done in parts of the world where carbon dioxide is accumulated and pumped into geological storage reservoirs. It is happening in practice in Norway. It is happening in North America. There is some talk of tests in this country. And one of the big advantages that Sasol would have there is that probably 2/3 of its carbon is already concentrated in a 100% concentrated CO2 stream. The carbon coming out of most power stations is very dilute because it is burnt with air, and it is mixed in the flue gas with air and everything. So there are possibilities. There are big challenges, but I think there are certainly opportunities for a innovative technical company here.
Thank you, John. Rob, can I ask a further question, a rider to that one, which is fuel, petrol. Is that an appreciable contributor to the profits, to the ability of Sasol to continue, or are the side products now taking over from that, would you say?
It's hard to say.
Sorry about that.
In South Africa, all of Sasol's products come from coal. And you can imagine that just, Rosemary, you probably know better than I, a ton of coal probably costs about 100 Rand a ton today. It may be 200, I don't know what it is. But a ton of petrol, but without the taxes, is probably in the order of 1,000 Rand. I'd just say 10 times as much, maybe a bit more than that. But if you get to a ton of polyethylene or polypropylene or alpha olefins, or these things, they're then 3, 4, 5 times higher than that again. So secrecy is, to me, is the full value chain, not just one or other part of it.
Yeah. Thank you.
Thanks, John. Thank you, Tony.
Could I interject? It's John Dolby here.
Alan, to say, give you thanks. I think there is a little thank you from Rosemary saying, John, an amazing summary of world-class research and delivery, so much of which you led. Congratulations on a fantastic talk. But Alan, can I go over to you to say a few thank yous to John?
Thank you. Thank you, Rob. Am I on air?
You're on air and we can see you.
Thank you. Oh, in 2 ways. Thank you, John. That was a fascinating insight into Sasol. And I think for most of the people watching our generation, gave new life to a household name that we've lived with all our years. And the development of Sasol obviously was happening in parallel to increasingly hostile political world, which makes, it's a huge credit to its leadership and the people there. And particularly, it seems like taking these huge risks very quickly and so confident of what they could do and would do, which is really, outstanding. And I think that's why it's so successful even today. And I think, for a long time, South Africa had a proud record as a core competence. We were project managers of the world, in mining and also big plants like this, and on a scale that is quite unbelievable. And the risks, as we said, must have caused you a lot of sleepless nights when you take theory and put it into practice, and now you've blown billions. It must have certainly shortened your life, John. Anyway, but what I would like to say at the end is that for a propeller head like you, you decoded that into something like somebody like me could understand perfectly. And I really enjoyed it. And U3A, as usual, would like to send a small thank you. That'll be in the post this time, John. I can't hand it to you. But so look at your post box. But thank you once again from all of us for a really interesting evening. Thank you.
Thank you very much.
Thank you.
Thank you, John. That was fantastic. Lionel and Rosemary.
Thanks, John. Shall I put you back as the, or should we just switch off now? Okay. Thank you very much, everybody. Thanks for attending. And thank you, John.
Thank you, John.
Thank you very much. Very